So last class we were talking about the conditions that a force field should satisfy for it to be a conservative force field. And we determined that this was the case. So if we had a particle of mass m that was being transported from point A to point B, say along path S1, and if for some reason we decided that we didn't like that path and took a whole different path, just call it S2, then for this force field to be a conservative force field, then if you took the integral from point A to point B of f dot ds1, then if the force field was conservative, then this would be exactly the same as taking the integral from point A to point B of f along path number 2. Now, these paths can be whatever paths, so you can pretty much decide which one to take. And if you test all the possible paths and those integrals happen to be the same, then the force field is conservative. Even more, if you had a point A and you say, for example, I don't know, took a walk around a closed path S, then for the force to be conservative, equivalently, then the integral of f dot ds along this closed path should give you 0. And when I mean along this path, it can mean any path. So to determine if a force was conservative, a force field was conservative, using this method, then you would have to try an infinite number of paths that it's pretty much not practical. Now, there's a theory from mathematics called Stokes' theorem that helps us solve this mystery. And pretty much we determined that if a force field was conservative, then mainly two conditions should be satisfied. And the first condition was that the curl of the force field should equal 0. That is the first condition, and it's a must for the force field to be conservative. Now, the second condition is a little bit easier to determine, and is that the force field cannot depend on time. That is, the force field can only be a variable of x, y, and z. So if this force meets these two conditions, then we say that the force is conservative. Now, this has a very, very deep and important implication, and is that, if the force is conservative, then this force can be written as the negative gradient of a function phi that depends on x, y, and z, and this function phi is called the potential energy function. Notice that I could have said that this was only the gradient of a function, of a scalar function without any negative sign, but here we have a negative sign, and this is one of the goals for this class, to see what the meaning of that negative sign is, and also to find this potential function given a conservative force field, and given a potential, find the force. So find the force with the potential, find the potential with the force. That's the goal for this class. So last class we proved that in general the final kinetic energy, that is 1/2 b final squared minus 1/2 of m b initial squared, is equal to the integral from an initial point to a final point of the net force dot producted with the path, with the vector that's always tangent to the path, and this is called the work done by a force by a force field, important, by a force field of transporting, of moving, of transporting an object of mass m from a point x1 or x initial to a point x final along a path S. And so this means that if I have a point that's labeled by x initial and a different point that's labeled by x final, then I will take my object of mass m along a path where I have to put an arrow indicating the direction of the path, and this path is labeled as S. That's all it means. Now we must remember that this net force can always be written as the sum of the conservative forces plus the sum of all the non-conservative forces. F non-conservative, and pretty much we know that F cons is going to be a conservative force, and F non-conservative is going to be a non-conservative force. Now we must remember that each force, conservative or not, or non-conservative, right, can be a function of the position, that is of x, y, and z, and to some extent it can be a function of the time, and this is pretty much what's called a vector force field, or just a force field, depends on what text you're using. Or just a force field, and the meaning of a force field in more mathematical terms is a collection of vectors that represent the force felt by a body or by an object at a point in space you can label it as x, y, z at a given time t. And that pretty much defines the type of force that you're applying. If the force does not depend on time, the force might be a conservative force, and if the force does depend on time, it's definitely not a conservative force, and we will look at the reasons why this is. So the meaning of a force, depending on the position and time, right? So if F depends on x, y, z, and t, this only means that the components of the force, that the vector components of the force themselves depend on x, y, and z. So for example, if I have this kind of force, I can say that the x component depends on x, y, z, and t in the I direction, plus some other independent force in the y direction, that's also a function of x, y, z, and t, and in the j direction, plus some force in the z direction with components x, y, z, and t, or that depends on x, y, z, and t in the k direction. And so this means that the components of F of the force depend on the position and time. on the position and time. And of course, we want to give some properties of conservative forces. And I will just enumerate them. This we have already seen, but there's a property that states that it cannot depend on time. So the force field cannot depend on time. And a little bit more mathematically speaking, if the force depends on time, then what happens is the path that we take, the path S that we take, must be parametrized in terms of the time. In terms of the time variable, and this means physically that there is energy or work done being input to change the field. Now that's all it means. So there's really no conservation of energy, as we will see. And the second condition that must be satisfied for the force to be conservative is that the curl of the force field must be zero, and we must say that the force must not depend on time. So if the force does not depend on time, then the curl of F must be equal to 0. Those are the properties of a conservative force. But now we have two questions. Well, now that we have seen all of these conservative forces in all these properties of conservative forces, well, question is, how does a vector force field look like, right? That's one of the questions. That's the first question. And actually, the second question is, well, I've been talking about the curl. So how do you take the curl of a vector force field? So these two questions are very important questions, and it's some questions that we will answer in the next section. This is an example of how a vector force field looks like. So notice that the arrows in space are not uniform, and they can depend on the coordinates. So in this case, the force field, it's very unclear just from looking at it how it behaves. But if you were to use a plotting program, then you would get a nice picture like this. And I encourage you to try to, look at all this different force fields that you can find. I encourage you to look, say, for example, at the gravitational field that sooner or later we will take a look at. But some very nice representations can be made with this kind of software. So now the question is, well, how do you take the curl of a vector field? So how do you take the curl of a vector field. And that is a very important question, since it is how we calculate things, how we prove that a field is conservative or not. Now we will define the gradient as an operator, as we have already done so, as dx dy dou c, where this can be set into unit vector form. At least when you're working in Cartesian coordinates, it's easier to represent it like that. So this can be written in terms of unit vectors like this. And I am using the notation that the alpha is just the derivative with respect to alpha of whatever function you apply it to. So say, for example, I want to take the partial derivative with respect to x of f of x, y, and c. Then this is equivalent of taking the partial derivative with respect to x of x, y, and c. This is all this notation means, and it's a shorthand notation, and it's a very nice notation. It pretty much compresses the amount of space that you would need to write. So just keep it in mind when you are reading books. This is a notation that it's frequently used. So as I have already defined, say that f, this force field, was a function of x, y, and z, and we wrote it as fx of x, y, c in the I direction, plus some f of y in the x that depends on x, y, c, and j, plus some f of c, x, y, c, and in the k direction, right? So we have our force field. And just for notation purposes, and again for ease of notation, then I will just write it as this components, as the functions without the x, y, z, but it will be understood that that this force fields, this components, right? So for example, this one depends on x, y, and z, same as say this one, and same as this one. They all depend on x, y, and z, and we already know that if a force is conservative, it cannot depend on time. So we're gonna deal with conservative forces and define what a curl looks like. At the very least, what how you take the curl of a function that does not depend on time. So if you take the curl of your vector field f, then this can be done by taking the determinant I, j, k, and here you place the partial derivatives, and then here you place the functions x, y, and z, and you take this determinant. So if you do this, then the curl of f will be taking the determinant. Now notice that in this case the order matters, since this quantity, let me see, this quantity nabla is pretty much an operator, right? And it's not a vector as such, but it's a vector operator. That means that it acts on vectors and gives you back a different kind of vector, different vector. That's what a vector operator is. And so vector differential operator is, because you also have vector integral operators, but that's a whole different story. However, though, when you want to take this derivatives or this curl, you again start with the first row. So let's start with this one, right? So we take the partial derivative with respect to y of f of c, and we subtract the partial derivative of c with respect to y in the I direction, right? That's one term. And then you must add the second term. So for the second term, you take again, you take this minor, the determinant of this minor, and you remember that you have to flip the sign. So this is partial c of f of x minus partial x of f of c in the j direction. And finally, you take the last the determinant of the last minor matrix. Again, remembering that you have to flip the sign from the previous one. So this is del x, del y, del x, del y minus del y, del x, and this is in the k direction. So now you have kind of like a formula for this. Let me just rewrite this so that it's a little bit more clear. This is I, j, and k, partial x, partial y, and partial c of fx, fy, and fc, right? So that's how you take the curl of a function, and we shall give an example in the on how to take the curl of a very specific field, in particular of the field we just saw.